Okay, so far we've been dealing with the following setup where uh, we want to compress a source, which we've assumed is some symbol coming from an alphabet X. We assume that X is distributed according to Px, and this is encoded, compressed to get a k-length code word sequence, which can be decoded to get back X. And k is a function of X. But we've assumed so far that both the encoder and decoder know the distribution Px, right? And we know that the optimal expected length, the best that we can hope to achieve, is between h of x and h of x plus 1. In the case where, okay, so even before that, uh, so we've assumed that Px is known to both the encoder and the decoder, and we've seen three different compression algorithms: the Shannon algorithm, the Huffman codes, and the Shannon-Fano-Elias codes, which get you close to the entropy, most h of x plus 1, or h of x plus 2 bits. Right? And we've seen that if the encoder does not know Px exactly, but instead uses Qx for encoding, then the additional price that you have to pay is dpq, right? So the best possible compression length that you can achieve is h of px plus dpq. Right? So if I use the Shannon code, then the compression length that I can achieve is greater than or equal to h of px plus dpq, and is less than or equal to h of x plus dpq plus 1 bits. Okay, and this is for a single symbol. Now, if we do symbol-wise encoding, then the best possible compression length, expected compression length that you can achieve is close to h of x bits. Of course, assuming that both the encoder and the decoder know px exactly. Sorry, the compression length is n times h of x. If we do symbol-wise encoding, but on the other hand, if we do block-wise encoding, we can get close to h of xn. So h of xn plus some constant. In this case, it is n h of x plus some constant. This is symbol-wise encoding. Xn. If we try to encode the entire block of n symbols, that is, we design a compression algorithm for uh, n symbol for a block of length n, then we can get to h of xn plus alpha bits. All right, but of course, all of these are on the assumption that we know px. And as I mentioned earlier, one way, even though we don't know px, if n is sufficiently large, then we can estimate px reliably by looking at the empirical frequencies and constructing the code using the empirical frequencies. Right? But on the other hand, blockwise encoding is not always good, and ultimately, even if we want to achieve the if we want to achieve h of xn, so even if we do estimate the empirical frequencies correctly, we can still only get to n times h of x plus alpha bits. If we want to get to h of xn plus alpha bits, or h of some xb plus alpha bits, then we'll need to compute the empirical probabilities of all possible b length sequences. Right? So all possible. So this h of xb for any b greater than or equal to 1 would depend on the empirical frequencies of xb. Right? And if b is close to n, then your estimate would not be very reliable. All right. Okay. So the goal in the next couple of classes will be to design compression algorithms which still get you a good enough expected length, or at least a small enough average rate without knowing px a priori. So we'll design so-called universal compression algorithms which work without knowledge of px or pxn and still get you close to the entropy. Okay. But before we get to that, any questions regarding the topics that we've covered so far? Yes, any questions? Okay. So before I describe these universal compression algorithms, let us think about the way we constructed these codes, or how we would construct these codes. Right. So the approach. So what was our approach so far? We first assume that we don't know xn, or I mean we don't know the distribution. So what do? We first observe x1, x2, x3 up to xn. Maybe it's of the form a, b, c, a, b, c, a, b, c, a, b, c, a, b, c. Okay. Let us suppose that this is the sequence that we observe. Okay. So what do? We first find the fraction of or the relative frequency of occurrence of each symbol in the sequence. So what is the relative frequency of occurrence of each symbol in this particular sequence over here? Yes, it's 1/3, right? So all symbols occur with frequency 1/3. Okay, so we observe this sequence, and then using these probabilities, we then go about designing a code. It could either be the Shannon code, or the Shannon-Fano-Elias code, or the Huffman code, or maybe even the arithmetic code. Okay, so using this, we construct code. So we would estimate this. That would be the first step. The second step would be construct code using this estimate, relative frequencies p hat, and then use this to encode. Right? So that would be our approach in order to compress this particular sequence. So so if I try to design a Huffman code, then for this particular sequence, what would it look like? 0 1 0 1 1 would be one potential Huffman code. Right? So maybe A gets the symbol 0, so code word A gets mapped to the code word 0, B gets mapped to the code word 1 1, and C gets mapped to the code word 1 0. Okay, so the encoding of this particular sequence, A B C, 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 and so on. Okay, so let's say I do this. I have 0 1 1 1 0 0 1 1 1 0 0 1 1 1 0 0 1 1 1 0, and so on. Right. So what is the expected length over here? Or in other words, if ABC 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 and so on repeats, say 100 times, right? What is the length of the compressed sequence? Using this Huffman code? Right? So each ABC requires a total of 5 bits to represent. So if this is so there are actually 300 source symbols, and you would need 500 bits to represent this. Right? So k of xn is 500 bits. Now, is there a better way to do this? So of course, so this is 500. So the total compressed length would be 500 bits plus some bits needed to represent p hat for p hat, right? So because you need to encode p hat in the header. So the header plus 500 bits would be the total length of the compressed file. Now, is there a better way to do this? Given that this is the sequence observed, is there a way of compressing this so that it takes less than 500 bits to represent? I'm not looking for, like, say, Huffman code or Shannon code or Shannon-Fan alias code or anything. Can you just give me a representation of this, which will require less than 500 bits to represent?
So we can use the frequency of that particular sequence before a sequence. Let's say we can encode 300 in binary and place it before ABC.
Oh, so you're saying you encode the entire 300 length binary sequence?
No, sir. The number
No?
300 in binary. Like
Okay.
300 binary representation followed by ABC. Now we have how many times it repeats and then the sequence.
Sorry, the number of times what repeats?
The sequence ABC repeats.
Okay. So this particular thing could be represented in the following way. So to sort of rephrase that answer, you could store p hat of ABC, right? So look at all possible 3-length sequences. You know that p hat of ABC is equal to 1. So obviously this keeps repeating itself. And then you need some way of encoding, so saying that it is only ABC which repeats. So you do blockwise encoding of 3 symbols at a time, and then say that p hat of ABC equal to 1, and therefore all you need to do is encode the length of the sequence and this particular probabilities, right? So the decoder will first see that, okay, there are 300 symbols of length 3, sorry, there are 100 symbols of length 3, and then p hat of ABC is equal to 1, so that is enough information to say that it is just a sequence of ABCs. But of course, this works only for this particular sequence because we already know that ABC keeps repeating. For a general sequence, you need a slightly different way of encoding. So the point that I'm trying to make over here is that this is an example of a sequence which is not IID, right? In this particular sequence, the relative frequency of A is 1/3, relative frequency of B is 1/3, relative frequency of C is 1/3. So if we did symbol-wise encoding, even using Huffman codes, we would get a large expected length of 500 bits. But on the other hand, there is a lot of redundancy in this particular sequence because after all, it's just a sequence, it's just a repetition of ABC over and over again, right? And of course, for this particular sequence, there is a better representation. You just encode that ABC is repeating 100 times, and that is good enough. But this works for this particular sequence, and we can't possibly go about designing a different compression algorithm for each sequence, right? So we need a generic compression algorithm which can somehow account for or which can somehow compress sequences even though there are long range redundancies in the sequence. All right. So our approach that the approach that we used so far doesn't work for sequences which have long range dependencies. Right? So they work very well for IID like sequences, but then if there is redundancy of this particular form, then it doesn't do that. It gives a large compression length. So the question is, can we do better? So if we think about it, there is a slightly different way, or another way of describing the compression algorithms that we used so far is that basically what you do is you construct a dictionary, right? So for example, if you're using a Huffman code, then your dictionary would be all possible symbols. If you did symbol-wise encoding, then the dictionary would be all possible symbols that you can observe and the corresponding code words. So A0, B10, or B11, right? B11, C10. Okay, so this would be your dictionary. After all, you need to know what symbols are being encoded, and corresponding to the dictionary, which consists of the symbols and the corresponding code words, you can encode and decode. So the encoder looks at this dictionary. So given the sequence x1, x2, x3 up to xn, it looks at the dictionary, and then when it sees a 0, it replaces this with when it sees an A, it replaces it with 0. Whenever it sees a B, it replaces the B with 1, 1. And whenever it sees a C, it replaces C with 1, 0. And that is how you get the code word. Right? So this technique could be generalized. So this dictionary could be something arbitrary. So one way of designing a compression algorithm is the dictionary could consist of sequences or subsequences which repeat very often. All right. So let me call this a phrase. That. Okay. So the dictionary consists of all possible phrases. By phrase, I just mean a subsequence. Okay, and corresponding to each phrase in the dictionary, I need to assign a particular code word. So in this particular example, maybe the possible phrases that I observe are ABC. Maybe there is BAC and CDC. Maybe these three. I have a sequence where only these three phrases are observed. ABC occurs most often. BAC occurs less frequently than ABC, and CDC occurs less frequently than BAC. Okay, suppose that these are the only three kinds of phrases that I observe in the sequence. Then I could assign a code word of one for the phrase ABC and 10 for BAC and 11 for CDC. So for example, my sequence could look like this: ABC, BAC, CDC, ABC, ABC, CDC, BAC, and so on. Okay, so maybe this is the sequence that I observe. I can just encode it using this particular rule. Okay, so let me generalize it even slightly further. Suppose that my sequence consists of the following phrases: ABC, ABC, BA, ABC, BA, BA, ABC, CDC, so on. Okay, so it consists of only the following phrases: ABC, ABC, BA, and CDC. You don't really have any other phrase. Okay, sure. So one way, right? So the dictionary would consist of all possible phrases for which we have a code word, which in this particular condition, in this particular case, would be ABC, BA, and CDC. Okay. Now these are all special cases. I'm not really telling you how do you identify the phrases yet. Okay. Now, if I want now a good compression algorithm should assign shorter codes or smaller code words to phrases which occur more often, and longer code words to phrases which occur less often. So I could assign, say, 1, 0, 1, and 0, 0 to as code words corresponding to the phrases ABC, BA, and CDC. Right? So right now I'm just giving you some intuition. I haven't really given you a particular algorithm yet. Okay, the high level idea is that one way to construct a compression algorithm would be to design this particular dictionary of different phrases, which could be of possibly different lengths, and assign code words to each of the phrases in this particular dictionary. Okay, and that is the kind of algorithm which it turns out will let us obtain an average rate equal to the entropy rate. Okay, so I'm going to describe a class of algorithms, or two different algorithms, what are called the Lempel-Ziv algorithm. It's actually two algorithms designed by the same group of people, Abraham Lempel and Jacob Ziv. Abraham Lempel and Jacob Ziv. So they gave two different compression algorithms, one in 1977 and one in 1978. So these are like really old algorithms. So the algorithm which was designed in 1977 is now called the LZ77 algorithm. So basically the last names of the authors and the year in which it was designed, or the year in which the paper was published, and the other is called the LZ78 algorithm. And the LZ77 and LZ78 algorithm are sort of basic building blocks of most modern compression algorithms, including gzip and zip and so on. Okay. So the basic idea of the Lempel-Ziv class of algorithms is to construct this dictionary. So you don't use a predetermined dictionary, you construct the dictionary after observing the sequence. Okay? So the idea is the following: given a particular sequence, given a particular observed sequence, right? You first partition the sequence into phrases. Okay, so maybe this is one partition. Okay, the LZ algorithms actually give so there is a rule as to how you partition the sequence into phrases, but but at a high level you partition the sequence into phrases and then encode each phrase. So how do we partition the sequence into phrases? So in the LZ77 algorithm, the way you partition into phrases is the following. So you start by looking, so you start from the first symbol x1 and then you keep going on from x1 all the way to xn. Okay, and then you keep dividing into phrases. So the algorithm works in sort of an inductive manner. Suppose that we have already partitioned x1 through xi into phrases. Okay, so now I'm going to tell you how do you assign the next phrase. So the first phrase is always x1. Okay, so the description is going to be inductive. So the first phrase is just the first symbol x1. Okay, and the rule is the following. Suppose that we've already partitioned x1 through xi into phrases. This is how you would generate the next phrase. So the next phrase is, so look at the longest subsequence starting from xi. So the longest subsequence xi plus 1 up to xi plus l, such that such that this subsequence is present in x1 through xi. In x1 through xi. Okay, so what does this mean? So xi plus 1, xi plus l. So this particular subsequence has already been observed somewhere over here. So for example, if this is A, B, C, D, A, B, C, then it must be that I've already seen A, B, C, D, A, B. So A, B, C, D, A, B, C occurs as a subsequence somewhere before xi. Okay, so that is the rule. Okay, so it's the longest possible sequences. So if I look at xi plus l plus 1, then this does not occur anywhere before this. Okay. Now it's possible that you don't see any match at all. Okay, so if xi is a new symbol which has not been observed, sorry, if xi plus 1 is a new symbol, then the next phrase is xi itself. Okay. So let's see an example to understand this better. A B. Okay, suppose that this is my sequence. Okay, my goal is to partition this sequence into a number of phrases. So as the rule says, the first phrase is always the first symbol. So this is going to, so just A is going to be my first phrase. Okay, now let's look at the next symbol, B. Have I seen B before? I have not. So the next phrase is just B. Okay. Now let us look at the next symbol. Have I seen A before? Yes. Question?
Sure. Shouldn't at the second point, uh, shouldn't it be xi plus 1?
Oh, sorry. So this should be xi plus 1. Thanks for correcting. Yeah, so the next phrase is just xi plus 1. Okay, so coming back. So we've already got the first two phrases. Now let's look at the next symbol, A. Have I seen A before? Yes, I have seen A before, and I have seen it over here. But have I seen AA before? I have not. Right? So the next phrase is just A. It is A. Okay. So now let's look at the next symbol. Have I seen A before? I have. Have I seen AB before? I have. I have AB over here. Right? Have I seen ABC before? I have not. There's no ABC before this. So the longest phrase which we've seen before is AB, and that is going to be the next phrase. AB. Okay. Have I seen C before? I haven't. So this becomes the next phrase. Do I have A before this? Yes, I have seen A before. Have I seen AB before this? Yes, there is AB over here and AB over here. Have I seen ABC before? Yes, there is an ABC over here. Have I seen an ABCD before? No, I haven't. So ABC is the longest phrase that I've seen so far. So ABC is going to be my next phrase. And then D will be the next phrase, and AA will be the next phrase. Okay. So, right. So any questions? Yes.
In the third like after A, B, and then A can be another one, right?
No, right? I have
AA
not.
together.
I have not seen AA before, right?
So that should be third one, right?
No, right? So it is the longest subsequence which has been seen before,
Okay.
right? So prior to this point, I have only A. I don't have an AA occurring before this, right?
Yes, sir.
So just A is going to be the next phrase.
Okay.
Okay. But on the other hand, let's say I'm at this point. So ABC is the longest match which I can find in this region over here. because ABC matches with this.
Yes, sir.
All right. Uh, any other questions? Okay, so let's do some more examples. Now, say that I have the following sequence, A, B, A, A, B, C, A, B, C, D. Okay. Now, can you tell me what is the partition of this sequence into phrases according to the rule? Okay, so let's maybe do this step by step. So what is the first phrase? A, right? So A is going to be the first phrase. Now, what is the second phrase? It is just going to be A, right? Because we've only seen A so far. What is the third phrase? AA, right? So we are at this particular point, right? So this is our xi plus 1. And we have seen A before. We've also seen AA before. It matches with this, right? So the next, but we have not seen AAA before. The longest match is only AA. Okay, so the next is going to be AA. The next phrase, what is the next phrase? Just A. The next phrase is B. The next phrase, it is C. The next phrase, it's A, B, C, right? We're at this particular point over here. And the longest match that we can find, we've seen A, we've seen B, we have seen ABC. There's a match over here, but not ABCD. So the next phrase is ABC. The next phrase is D. The next phrase is D. The next phrase, D again. And the next phrase is A. Okay, so this is what we would get if we partition the sequence into phrases using the LZ77 rule. Okay, let's take one more example. Say we have this A, 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 A. Okay, so you have full repetition. Right? What is the first phrase? It is just A. The second phrase, A. Third phrase is AA. Fourth phrase is, so what is the longest match? So we're here, right? So the longest match is with 4 A's, right? So that is going to be our fourth phrase. Now if this continues, A, then what would be the next phrase? How many A's would it be? It would be 8 A's, right? Because that is the length of the sequence so far. So 8 A's would be the next, and so on. Right? So if it's a sequence of all A's, right? So the first phrase would be an A of length 1, the second phrase would be an A of length 1, third would be a A of length 2, fourth would be of length 4, fifth would be of length 8. So in general, if you look at the ith phrase, what would be the length of the ith phrase? If it's a sequence of just all A's. Okay, and why is it 2 to the I minus 2? Or some people who say 2 to the I plus 2, and so on. Right? Can someone tell me why it is 2 to the I minus 2? Yes?
So when I equal to 2, when I equal to 3, we are getting 2. So it is 2 power 3 minus
Okay.
2. So when I equal
Okay.
to 4, it is 2 power 4 minus 2. When I equal to 5, it is
Okay. So what is the next going to be? So it's going to be 16, right? Right. So okay, so by induction we can say this. So in general, if so, what is the ith length of the ith phrase going to be equal to? It is a sum of the lengths of the phrases before that, right? So okay, so I'd like one of you to put up a proof of this statement on Piazza later on. Okay. All right. So it's 2 to the I minus 2. Well, it is whatever max I minus 2, 1. Okay, so this is how the Lempel-Ziv algorithm or the LZ77 algorithm partitions the sequence into phrases. Now that we have sort of partitioned the sequence into phrases, we need a way to encode each phrase, right? After all, we want to compress the sequence. So how do we encode each phrase? Each phrase So how do we encode each phrase? Now there are two conditions. One, there is a match. The second, there is no match. Right? So in case one, when there is a match, all you need to do is give a pointer to location where there is a match. So maybe xi plus 1, xi plus 2. So it should be plus 1, plus 2, and so on. Xi plus L matches with xj plus 1, xj plus 2 up to xj plus L. Okay, where j is something which is less than I. Okay, so in the first case, you need to store a pointer, which is basically just store j, and then the length of the match. So this pointer is basically the location of the match, and the length of the match, L, right? And we'll store an additional bit 0, to just indicate that this is there is a match. Okay, so match equal to yes, then the location, and then the length of the match. Okay, so that is in the first case. Now what happens in the second case? In the second case, there is no match, so all you need to store is 1, which is no match, and the new symbol. So xi plus 1 has not been seen before, so binary encoding of xi plus 1. All right. So this is an encoding. I mean, I have not really given the binary encoding of each phrase yet, but this is basically the information that is required in order to reconstruct the sequence. If we have this much of information, then we can reconstruct the source sequence from the encoding of each phrase. Right? So this is the information about each phrase that we need to encode. Any questions?
So when there is a match, won't it be better if we use minimum of both? Let's say binary encoding of
Yes.
sorry, nothing.
All right. So there is a match, right? So okay. So I guess you're talking about this particular case where you have after an A you have an A, right? So it seems that this would take more space than just this. Is that what you're concerned about?
Yes, sir.
That's okay, because ultimately we'll be interested in sort of minimizing the expected length of a large sequence. So the number of symbols will be far less than the length of the sequence itself. So of course, it would maybe be better to encode it this way, but ultimately it won't matter. It's just a small overhead.
Yes, thank you.
Okay. All right. So before I forget, we'll have a yeah, sure. For the first phrase, maybe we don't require a match bit, but just to be consistent, we will always the first phrase will be encoded by 1 and then the binary encoding. Okay. Although, yeah, so you can always do small engineering optimizations because there are some information which are redundant, but this is the rule. Okay, so this is the rule that we will use. Okay, so here's the quiz. It's a very short quiz for today. Let me know in case you have not got the quiz link. If you're not able to access the link, then just let me know. So ultimately the location will, so all of these will have to be stored in binary, and in the next class we'll discuss how exactly we are going to store this in binary. We need a more intelligent way of storing it. two of the options are repeated? No, they are not. They're all different. Yeah, read the question carefully. So you can take maybe 1 more minute to give your question, submit your solutions. Is there anyone yet to submit your answer? Anyone yet to submit the quiz? Okay, so I'll stop accepting responses. So the Shannon code assigns, so if we assign code word lengths of log 1 over q of x, then this is greater than or equal to log 1 over q of x and less than or equal to log 1 over q of x. So the expected length is going to be so summation p of x log 1 over q of x, and p of x log 1 over q of x plus 1. So this is h of px plus dpq, and this is h of px plus dpq plus 1, right? Okay, so anyway, we end the class for today. In case there are a couple of questions, I can answer them here, but otherwise we'll meet on Wednesday.